Okay, chapter 22, day 2 video, which is a new topic. Day 2 during class, we did the practice problems with confidence intervals. Today's video is going to be looking at something new. We're going to look at a hypothesis test, but for the difference in two proportions. We did a hypothesis test already for one proportion being greater than, less than, or different than some number, but now we have a hypothesis test about a difference in proportions. And so we start out with our null hypothesis. Our null hypothesis is basically the same every time, which is P1 and P2 are the same. Now notice, I'm not using the hats, I'm using the true proportion P of group 1 equal to the true proportion of group 2. What that really is saying is the difference is 0. So our null hypothesis is that they're equal or they have no difference. On your calculator you'll see P1 equal to P2, okay? Again, our alternative. Just like we had the boys and the girls with green eyes. We might say that the boys have a higher proportion than the girls, in which then it would be a one-tailed test upper. We might say the boys have a lower proportion than the girls, one-tailed test lower. Or you might just ask, is there a difference between boys and girls? In which then that is the not equal to condition, which is the two-tailed test. And again, if you were reading this from the back of the book, when you got to this value, either high or low, you would have to double it to get your p-value. Most of us aren't choosing to use the back of our book, we're using our calculator. The calculator gives you the doubled value automatically. So again, alternatives, group 1's higher than group 2, the proportion of it. Group 1's less than group 2, group 1 not equal to. But just like before, we better define who's population 1 and who's population 2, otherwise these have no meaning. And so you must define population 1 and population 2. Okay? Well, if we're going to use normal calculations, you got to check our conditions. So just like before, state your HO, your HA. Next, check our conditions. I know what you're saying, but here's the good news. Condition 1, 2, and 3 are the same for confidence intervals. Randomization, representative sample, independence between, independence within. So you're actually going to do them, but what I'm saying is they're the same, they're not different. Same as the ones we use for confidence interval. Okay? The last condition though is slightly different, and it's based on what's behind my back here. If my null hypothesis really is that the two groups have the same proportion, then are they any different? No. So for example, I have a certain number of girls out of total and a certain number of boys out of total that have green eyes. Well, if they truly are the same, can't I just lump them all together and say how many kids have green eyes out of how many kids total? And because of that fact that our initial assumption will always be that they're the same, we can pool those together, and we're going to, not that we can, but we will pool those together and come up with one p-hat that is a pooled value of the successes for both out of the total for both. And so in our conditions, we have to use a pooled p-hat value. So it is the successes from groups 1 and 2 out of the totals. So for example, looking at the values that we had for our green-eyed problem, we pool we had 38 and 16. You're just going to pool those together and get a total. Out of, we had like 249 and 97 or something like that, or 246 and 97. You're going to pool those together. So we have a total number of kids with green eyes out of the total number of kids total, boys and girls combined. Gives us one p-hat value that's pooled. So, in your conditions, instead of using P1 and P2, you use the pooled p-hat. Because again, that is what's true. It's true that they're the same until we can disprove it. So, N1 times pooled p-hat, N1 times 1 minus the pooled. N2, got to check both sample sizes, because we don't always take the same sample size. N2 times the pooled, N2 times 1 minus the pooled, make sure they're both equal to, or greater than or equal to 10. When we do that, we say it's okay to do a two proportion Z test. Two proportion Z test. which on your calculator, I think is stat test 6. Let's check it out. Stat test. And if you look at number 6, the two proportion z test is the option you would pick. Notice, it has an x1 and an n1, and if you remember, these can't be decimals, right? x1, n1, x2, n2, so 38 out of 249, I think, boys, 16 out of 97 girls had the green eyes. And then our alternative hypothesis, are they not equal to? Is P1 less than P2? Is P1 greater than P2? And so just follow the sign that you have written in your alternative, okay? Well, we know the calculator does all the work for us, but we still have to show what we're doing. So standard error, again, like before, is the sum of each of the pieces squared. But we're not going to use P1 hat and P2 hat because our initial assumption is that they're the same. So we use a pooled P hat and a 1 minus pooled P hat over N1. Pooled P hat times 1 minus pooled P hat over N2. Add those together. And again, we really don't ever calculate this. We just substitute in the numbers. So initially in the problem, you've got to calculate yourself a pooled P hat to use. Now, when we lay out a normal curve, the 0 is always going to be in here, suggesting no difference. And then we can mark where our difference is compared to the 0 line. But basically, the z-score is the difference that we got minus our initial assumptions that they're the same, which is no difference, over standard error. So that turns into P1 hat minus P2 hat over standard error. Because really anything minus 0 is itself. So your difference divided by the standard error. Plug in the numbers. Plug in SE. I would do this, I would write this out separately somewhere, then just write SE right here. And go to your calculator and you'll get an answer. Okay, so if I'm using my calculator for our green-eyed person, and if you remember, we thought the girls were bigger than the boys, so let's see if they are statistically significantly bigger than the boys. In other words, boys are less than the girls. Let's see what it comes out to be. And let's see what this thing says. It gives us a z-score. It gives us a p-value, 0.38. Notice it gives us a P1 hat, a P2 hat, and this is our pooled P hat. And if I scroll down, because it's saying, hey, there's more, it gives me N1 and N2. Don't really need N1 and N2, but this is the important pooled P hat to make sure it matches what you had. So you could run the test, go back in and put this pooled P hat value into your formulas, as long as you state what pooled P hat is. Well, with a p-value of 0.38, which is greater than our rule of thumb, alpha 0.05, I'm going to fail to reject the null hypothesis. There doesn't appear to be enough evidence that I said that the girls had a higher proportion of green eyes than the boys, or the boys have a less proportion than the girls. And if you remember our confidence interval, let's do that, stat, test, I think we did B. Here's the beauty of this. They know that those two are linked, so they bring the data from the one into the other. And if you remember our confidence interval from day one, our interval spanned from negative to positive. 0 is in there. What did 0 suggest? No difference. It just kind of, the hypothesis test can go hand in hand with this, but it just kind of shows that they both confirm the fact that there's no difference. You write down your z formula, you write down the z off of the calculator, you write down the p-value off of the calculator, the conclusion is like old times. We're blank percent confident that, and so on. Less reject enough. And that's it. So when you come in next class, we're going to do the green-eyed person one in class and see if we can follow through this whole process. All right? And that's it for chapter 22.